morning section was canceled because the school opened for classes at 10 a.m. So what I decided to do, I don't want us to slow down or the two sections to go out of sync. So I asked students who could not come this afternoon for their section and those who were in the morning section to follow our lecture through Zoom. All right, so we have them on Zoom. And so what we're going to do today, practically solve problems, as we said. I mean, I started doing problems about Gauss's law and the divergence theorem on Wednesday in both sections. So today we continue. And then as we finish the problem that we have in front of us, then we are going to review what we have seen, and then I'll show you examples of where this information is very important. All right, because remember I told you that you don't necessarily need to solve very, very complex problems to find application into very complex circuits. A lot of times, the easiest solutions are the most meaningful and the most practical, all right? We normally use the easiest solutions to develop design rules, and then we use the most sophisticated solutions in Cadence or in HFSS or whatever else, just so that we can do a verification of our designs. All right, those difficult solutions and very extensive algorithms do not help in design. So you need to remember that. Okay, so today, if you remember what we covered a point charge and then field around it. We covered an infinite line charge and the field around it using cylindrical coordinates. Then we covered a spherical charge, all right, and we found the field. And today we are going to cover a planar charge. And in all cases, if you remember, our charge distributions or densities, rather, the charge densities were considered to be uniform, all right, just so we can find simple and meaningful solutions. In practice, that's not true, but as we said, these simple and meaningful solutions are extremely important. All right, so we did a three-dimensional charge, both at a point and distributed. We did a two-dimensional charge, a line charge rather, that is along a straight line and infinite. And now we are going to do a charge that is on a surface, but infinite surface. All right. In terms of why did I keep this for the end of those group of solutions? Because it's a little more complex, not really. I mean, very much simpler than what you probably may imagine, but a little more complex in the drawings and stuff. So I kept it last. So now what we have, as you can see here, is a surface. It's an XY surface. It's a planar surface. It's infinite long in both directions. And it has a charge which is uniformly distributed. And because that charge is a charge distribution, all right? If it's on a surface, obviously, it's going to have units of coulombs per meter square. If the surface is finite, same kind of shape, but finite, then I could give you a total charge. I could tell you that it is uniformly distributed and you could find the charge density. But since it's infinite, I cannot give you a total charge, all right? Because it's going to be infinitely large. So we are working with the charge density. And I put here the figure to see it. And obviously, as we have done in the past, we take a point, which is this one. And around that point, we create a small infinitesimal surface, which we call ds. And this infinitesimal surface, if you remember, always surfaces are vectors. So the vector infinitesimal surface is going to have direction and I have it below. Okay, I have already written it, so no need to do it twice. It's like this. Okay, it's here. All right, direction which is perpendicular to the surface. And in this particular case, it's a planar, we take it along the positive z direction. When the surface is closed, what did we say? The direction goes outward or from the volume the surface encloses, all right? But now since this one does not enclose anything, we just select the positive z direction for n. And n is here. Now, this surface is, what kind of symmetry does it have? Remember, it's infinite. Infinite. So, what kind of symmetry does it have? All right, you remember you have to identify the symmetries to be able to simplify things, all right? If we have a symmetry, then we can use Gauss's law. Without any particular symmetry, you cannot use Gauss's law. It's not going to give you what you want. But what kind of symmetry do we have here? Remember, to just get a sense of symmetry, you need to start thinking which direction, if I just change the surface, I'm going to see the same thing. Let's consider this. The surface is extending beyond what I have shown, all right? It's infinite. So for that particular surface, which is the axis of symmetry? Is it not Z? I mean, I can move this, it's an infinite surface, all right? Remember, it extends beyond what I have shaded, all right, here. It is the XY plane. The surface is identical. If you want to, as a matter of fact, write it here. The surface, the total surface is identical to the XY plane. All right, so you remember. What does that mean? That if I change the surface, I rotate it around the z-axis, I see the same thing. Do you not agree? Okay, so what kind of symmetry? Which is the axis of symmetry? Z. What kind of symmetry is that? Cylindrical, really, but because Z can be everywhere also, all right? It's not just one axis, Z can be anything. It's just that this surface, you can move it any way you want along the X and Z and X and Y. You cannot just, change it along the Z direction, but anything. So that implies, because that is true, then we know from the beginning that the X and Y components will not be important. Because if I can move the surface everywhere, anywhere, I mean, consider the ground, for example, to be this infinite surface, all right? Assume that this surface S is our floor here. And I'm walking, I'm trying to, it's an infinite floor and has the same charge, and I'm going around here trying to measure the electric field. It's gonna change, I can go from here there, and I'm gonna see the same thing. And since I'm going from here there, X and Y changes, and I'm seeing the same thing. What does that imply? That the electrical field is going to be independent of X and Y. All right. So that says it down here. All right. And as a matter of fact, I will highlight it so you can see it easily. Okay. Now, so we put things that we know, always. Two things that I would like to ask you. Read the problem every time very well. A lot of your questions to me before the homework is about things that are inside the description of the homework. All right, so for exams specifically, and for homework too, and exams more specifically. Read the problem well. Even if you have to spend 5 minutes to understand it, is well invested. Second, in our problems, we try to put down what we know. if you can make this a habit, then I'm telling you, you're gonna help yourself tremendously in identifying the solution. And especially as we go to more complex problems, all right? You have to put and say, what do I know? You write it, if that's what you have to do. 1, 2, 3 here. So 1 is that is independent of X and Y. Below that, what is it that we know? We know from Gauss's law, this is Gauss's law here. I don't put too many S's anyways. So from Gauss's law, we have that the divergence of D, all right, is equal to the charge density. At every point there is a charge density, and it's equal to 0 at every other point where there is no charge, all right? So that's what I'm saying here. The divergence of D is equal to surface charge density everywhere on the surface at any point. The charge density is a point charge. It applies at every point. So at every point on this surface, I have that relationship. But at any other point away from the surface is 0. Okay, these are the two things. So what is the third thing that we know? We know the divergence theorem. Now that we found some kind of symmetry, I can tell you we can apply Gauss's law. That's another thing that we've discussed, all right? So I'm ready to apply Gauss's law, and I'm remembering that to do that, I need to remember also, I need to recall the divergence theorem. What is the divergence theorem? It says that you can take, I'm not writing here the whole thing. Maybe I should. I think I have practically, it's all this one. It says, the first part of it, that if I take a volume integral of the divergence of D, that is equal to the surface integral that encloses this volume of D, all right? Inner product, of course, the surface, which is a vector. That's what the divergence theorem says. And of course, because of Gauss's law, we have, I will erase that for a moment and I will rewrite it, okay? So this is what the divergence theorem says. I will put it here because obviously I tried to speed up here and I did not do all of the steps. So this is one equation, divergence. Let me call this one 1, and this is 2. Okay, now, what do I do here? I mean, you could do something different, to tell you the truth. You could define any volume, all right? An arbitrary volume that encloses part of the surface. And on that, you could apply the divergence theorem. However, if you are in a given coordinate system, I'm not going to define an arbitrary volume, all right? I will define a volume that is easy to describe in that coordinate system. I have an XY coordinate system, all right? So I decided to define, since my surface is infinite, I will define a small volume. I call it delta V, okay? A small volume relatively to the surface. And I apply on this small volume, which looks like, you see, it's not a cube, it's a 3-dimensional parallelogram, all right? So this one is developed in a way that I can describe it in X, Y, and Z. That's why it looks like this. You remember how the volume was in the infinite line charge? It was like a cylinder, all right? But it was finite along the Z direction. So you always try to define your volume in a way you can describe it in your system. Here we can describe that, all right, in our XYZ. We don't necessarily have to do that, but it's important that you keep this in mind. So before then I move from equation 2, which is here, to anywhere else. let's also try to recall other things that we have seen. All right, so now you start going back into things that we have. Here is like we are building one brick at a time. All right, so down, if you look below you, there is a brick that is useful, like there is something we discussed. And I am going to place it here, so in a way that you can recall it. Do you remember when we talked about two charges, both positive? And then we try to find what happens to the field along the line that goes through the center of the two charges. And what did we say that happens to that field? At the center, but what happens along this line? It has only one direction, and what direction is that? The vertical direction. It goes like this. Because the horizontal, if this is your y or x, it does not matter. If this says your x coordinate, all right, and your two charges are along the x coordinate, and they're identical, and I go to at the center, I go to the point which divides the distance by 2, all right, the midpoint, and I draw a line which is vertical, perpendicular to the line of the two charges. Along this line, we found, and please go and read that, we found that the electric field at the center goes to 0, right, in between the two charges. But just above that point, it's not 0, and it's only along the z direction, because whatever horizontal components you have, they cancel out. All right, you remember that? Now it is important. Why is that important? Because I go back and say, okay, so now if I have this infinite surface, I can say that for any point on this surface, there is another point. Let's assume that I'm sitting here, all right? So now I'm sitting here, I'm trying to measure the field where I am. And so I say, if the surface is infinite, okay? So with relation to my position, half of the points of this infinite surface have another set of points that cancel their field right where I am, and especially at my length, it's going to be perpendicular in between the points. I'm not even in between the two charges, all right? They are below my feet, for example. In between the two of them, right below my feet, is going to be 0, but then at some point, as I'm measuring up, it becomes perpendicular to 0. You can argue that even when the value of the electric field is 0, still the direction is perpendicular to 0, all right? Direction perpendicular to 0. So since that happens for all of these points, that they have all of these other points on the surface, that they do that, that implies that this point where I am is perpendicular. Now I move another 2 feet here, and the same thing happens. All right, because this is an infinite surface. So what does that mean? That wherever I am, the electric field is going to be perpendicular to the surface. So the electric field, as you can see from here, is going to be along the z direction. So what I wanted to tell you is, what is interesting for electromagnetics, you remember that we are going to think physics first and then math. Math is not the goal. You're not running to math immediately. If that's what happens, you're going to find it difficult to come with a simple and accurate solution. You think physics first, all right? So you think, what is it that, how do charges behave, all right? I mean, this is the physical understanding of how electric fields at this point behave when you have different charges. That's what I want you to feel comfortable with, because if you remember the things that we have outlined, then practically you reduce the complexity of your problem. So at the end becomes like an obvious solution. The mathematics are so simple. So with that, what do I say then? Look at this. I say that now on this volume which I call delta V. The only place that I see an electric field is, of course, on everywhere, but only on these two surfaces, the electric field is parallel to the surface vector. In the other, perpendicular. In the other sides, on the sides, which are four surfaces, is parallel, okay? Is parallel to the surface, but perpendicular with the surface vector. Remember, the surface vector up and below has exactly the same direction. This is the direction of the surface, all right, for the surface ds here. This is the direction of the surface for the surface ds here, okay? And the fields on these two surfaces, therefore, are parallel to the direction of the surfaces. But on the sides, this is the direction of the surface here. On the sides, the direction of the surface here is this. And the direction of the surface here is this. And what happens to the fields on the sides, which are along this direction, are perpendicular to the surface. And why is that important? This is important because of this. Whenever your electric field is perpendicular to another vector, their inner product is zero, all right? You remember inner product is maximum when the two vectors are parallel, zero when the two vectors are perpendicular. So that tells me from here that if I were to write, which I will take it here, let me write this one. I'll copy. And let me also do the following, add here a page, okay. Place this, and then I will take this one, move it under here. Okay. So practically, I put here too. So here, from this equation too, in fact, I copied it, so practically it's 3 here, and then it's 4 down there. So when you read it, you don't get confused. All right, so from here, the second line, the second part of the equation tells me that practically we have 4 integrals on the sides where the inner product between B and the direction of those surfaces is 0. All right, so those integrals are 0. And then I have 1 integral on the upper surface. Let me call the lower surface ds prime just to, okay, let me put this one here. All right. Okay, so 1 is on the surface ds up there, or delta s. All right, so here, for example, delta s prime would be delta s. No. Let me see. I need to have the ds, so I will write this as n downwards, or at the direction, or minus az. Let me write that. It's minus az delta s. Delta s. All right, so let me give it that color. Okay, so here I have, and up here, delta s, which is up, is going to be az delta s. Okay, so I have also that one up here. So here it gives me, since the side integrals are 0, I'm going to have only two integrals on two surfaces, on delta S, which in fact is going to be dz ds, all right? Because there is only one, as you can see from here, there is only one component in E, and D is only the Z component, and therefore the inner product between D and ds is dz ds without the vectors. And the second has a minus from here, all right? And it's going to be a minus from there. And well, let me put it in here, inside. Delta S prime is going to be a minus from delta S prime, okay? And a minus from dz, because dz also below the surface has the outward direction. So a minus from ds there, ds prime. And then, so practically these two are giving me what you see below here, which I have it. So since I have it, here is this one. Okay, it's this one. So what you see here is in fact that I have now reduced my volume integral of divergence of d dv to these two surface integrals, which in fact, they give me nothing else but 2 dz delta s, okay? Now, I take that and then I look at, you remember the initial, where was that? Okay, let me right now go back since I found this from Gauss's law and the divergence theorem. So now I also remember that this one, delta V, divergence of d dv, was equal to what? Q sub s times delta V. All right? And as a matter of fact, Q sub s only exists on the plane. So that is going to be Q sub s delta s. All right? Q sub s is surface, does not exist within the whole volume, which means from this equation, star, I will name them later, and double star, I have there from above, what did I find? I found that 2d sub z delta s equals Q sub s delta s, which gives me something very interesting. And it's that d sub z equals Q sub s divided by 2. How about that? All right. So now, I don't necessarily need this one, but anyways, I'll clean it up before I put it up. Okay. And from there, because d sub z equals epsilon naught E sub z, what do we have? We have what you see below. We have that the surface excites a field that is constant at every point, independent of how far this point is from the surface, as long as it is not inside the surface, because there, all of the field is 0, you remember? Inside. As long as it's not inside the surface, everywhere outside of the surface is constant and has this value. So why is that important? I will then show you examples of where this is important, but also let us try to outline the three cases that we've seen. All right, what have we seen? Charges that are all accumulated in a finite volume. All right, so charges that are accumulated in a finite volume, corners, for example, I'll come to this, I'll show you some pictures, or other places where the charges go. Charges go normally to the most acute in space, if you like, place. All right. Have you seen this? The old days, they will do in physics. I never had that, but in physics, they will put a student on a chair. They will charge the student a little bit without touching the floor. And you will see all of these charges that will go to the hair of the person. So the hair is sticking like that. Have you seen when you try to comb your hair and it's like humid? So there are charges there and it goes out like this. So that's exactly what happens with charges. They go to like the smallest points. That's where they accumulate. So if you have charges like that, then the field that is contributed by these charges. So this is a finite charge. Okay. The field here goes, if this is the distance from the charge, the field goes down as 1 over distance. I put R because we use R so far, R squared. So for three-dimensional spaces, finite, it goes very fast away, which is good. If the charge is an infinite long line, or long enough, let me say this way, for the purposes of our class, say infinite long, and it's given by this, the charge, then if this is the distance from the charge, the field goes down, not exactly the same way. I have to correct one of the two. Let me make this faster. Like this. Okay, and this one does not go down as fast, goes as 1 over R. Okay, and then if it is a surface where the charge is distributed and is infinite long, so all right, I will do it here. The surface is, I don't know how else to show an infinite long surface. Then if this is your distance D, your electric field goes constant. These are the three things that we've seen. Why is that important? Any questions before I show you examples? Why when it's infinite plane or when it's large enough? Yes. The law. So because, so infinite does not apply in practice. What applies in practice is how small the distance that I have from the surface is from the size of the surface. So for all practical purposes, if, for example, I was here in a circuit and the surface was like this plus another this, it would, for me, practically, I would not see the charges at the edges. So that effect for those charges will be very small. So practically, if I were to walk around without going to the edges of a finite surface and the surface was very large, then I would see something like an infinite, which means no matter where I am, that if I am around here or if I am out there, the field will be the same. That's what it is. It's because of the dynamics of all of the charges and how they distribute. All right. But if it's on a line, the line may be a wire. If I have a wire that is out here, and then there are charges, and it's not shielded, all right, so the charge can radiate, then I move away from the wire, I will see the field, which I will measure, to go down as 1 over the distance. But if my charges is on this, here, all the charges in this box, and it radiates, and I move away from the box, then what I'm going to see is that the field goes down as 1 over the square of my distance from this. And it has to do with the way the charges interact with each other. But remember those three cases. Okay, any questions? Okay, so now I will show you this one. You remember that I said that those are important in circuit design? Do you want to see a simple circuit board? Have you seen something like this before? You guys? Okay. So what are those pink, red? The red ones are like conducting lines. All right. So here, for example, let me use this one and then make it thick. So these ones are two lines. All right. They send a current. What is a current? Like a charge that moves. They're lines. They have a charge. They're charges. All right. The charges are distributed. Okay. These two are lines. These are also lines. And as a matter of fact, these lines here, they also break into, it's like a tree. Okay. What is, now that you saw this, what is this one? You see that? We'll talk about this. Okay. So now I am a designer and I want to design those lines. All right. So practically, these lines are not infinitely thin, but they are wider. So if I follow this, that the field goes down as 1 over the distance, all right, for the charge that is accumulating at the on this line or runs through the line, practically I can find that the field that I will see, the impact I will see from one charge flowing along this direction and another charge that may go along the same direction. All right, so that the impact of the one line on the other is not going to be that important. Maybe it's 10% only, all right, because it's not just how it changes, it's also the coefficients you have on top. So if it's only 10% of my charge that I have on the other line, if they, what I call the crosstalk, all right, the crosstalk is the impact I have, the field that I feel because of another line, not the field that I have because of my own charge, for example, if I'm a line. Okay, so that tells you how close to bring them, because obviously in a circuit design, you want to use as small a space as possible. So ideally, you would like to bring them even closer, but this is a digital design. So for high frequencies, you will see that they're further apart, I'll give you, because high frequency effects are even more important. So that is one. Then the same thing applies when they look at these lines here. Okay, the two lines, as a matter of fact, not all three of them, but practically, not all three of them, but practically these two. Okay, so now you know that for these lines, you use the approximation that it goes as 1 over the distance. However, for these dimensions here, for these, excuse me, not dimensions, for these bends here, if there is accumulated charge, and usually as we will see later, that is called parasitic capacitance, it creates a parasitic capacitance, then your electric field, your crosstalk goes as 1 over distance squared. So I worry more about this, the coupling there, that I worry about this coupling, okay? So, but you see exactly where what we've learned makes sense. Now, I leave for last what we just learned, which is the ground. Do you see this one here? Okay, what do you see that there is a lot there? All of these holes. What do you think the holes do? Ground. They ground it. Why is that? We don't want to have charge on this plate. Why is that? Because if there was charge on this plate, I will see a very strong field, no matter how far away I was from this plate. And we mean even underneath it, all right? Not from the sides, but underneath it. Which means that if I have all of this charge, and then I don't do anything to get the charge out of the place, and I do it from grounding, all right? You remember grounding is like an infinite sea of negative charges. By grounding them, all of the electrons go and neutralize the positive charges. If I did not do that, then I would have serious problems in my circuits because of the fields due to that surface. This is the worst of all. And that's why you see the grounding here, and they have put many, as a matter of fact, I think there were too many, but they put enough holes to ground it. Okay, now let me go. I'll show you some other circuits. This is another circuit, high frequencies, higher frequencies, okay? What do you see here? There is a lot of going on. Do you see any grounds? No, they got rid of the grounds. How did they get rid of the grounds? They try to avoid them as much as they can. All right, if they need a ground, that they are gonna bring a via up. Do you see those here? The vias are like holes. They're gonna bring, and then they're gonna connect it directly. They're not gonna use a planar surface. This one, the first one I show you is an old design. The newer designs, you don't see those extensive surfaces. If I need a ground, I will put a ground right there. I'm not gonna have a surface to utilize as the ground, all right? So the only thing you see, however, are lines. And it's very funny on how the lines are connected. First of all, what do lines have? They don't have exactly sharp edges. If they don't have sharp edges, they do not concentrate charge there, all right? There is no point. If there is no point, the charges are not gonna go. They like the points, they like points. They go and concentrate on these things that they have these sharp edges. If there's no sharp edge on your line, you're not gonna have that problem. Second, yes, you do have lines that are close enough, and I'll use a different color. Here. You do have these lines, which are close enough, and you have the green lines, all right, which are going perpendicular. So these are different planes. If the lines go in parallel, depending on your frequency, if your frequency is very, very low, or it's a digital line, you can bring them closer. If your frequency is high, so you have an RF signal, you have to bring them further away. Also, if you don't want to couple them, you don't make them too long. So you will see there are lines that they are very short as they try to lay them out. So for example, look at these ones, all right? They don't let them run parallel for too long. Obviously, these ones are different types of lines. They have different types of signals. They don't care about this, but these ones, they make them short. And then the other lines, the green ones with the yellow, they put them perpendicular, because if they put them in parallel and they're at different layers, they're gonna have crosstalk, all right? So you place them like this, and then of course, each line goes away from the other, does not see much of a crosstalk there. So how does this work? The simple formulas are used as design rules. So then when you do your designs and you do verification, your tool is gonna come out and it will show you where you violated the design rules. So you have to go and correct it, all right? Because if you don't correct it, it's not gonna work. So that's how it is utilized. After you do your layout, you have to do a full verification, and then you really use other types of tools for full verification, where they have much more complex algorithms. But design rules are derived out of simpler solutions. This one, what happens when you have this kind of crosstalk? When you have charges that radiate parasitically, that they exert a field on another line, and then so change the signal that goes through the other line. Look at these ones. This is called switching noise. Especially it happens when you have pulses, or we turn on something. You have a switch, you turn on a switch, there is something that goes through, and then immediately you see the crosstalk that changes this. Or look at these pulses, how they have been altered because of this unwanted, all right, cross talk, we call it anymore. Here there is another circuit that shows, even in here, they have bigger grounds, but they put all of these vias. Anyways, so what I wanted to tell you with all of this is, you need to, what I want you to remember as you will solve problems is the three fundamental rules. An infinite large planar surface, the electric field that is radiated is, that is produced is a constant as you move away from the surface, the worse. If it's a line charge, it goes as 1 over the distance. If it's a finite 3D charge, it goes as 1 over the distance squared. So you remember that as we will try to solve this problem. So practically, I want you to remember the electric field from an infinite line charge, the electric field from a surface charge. Here, this is by line, surface, and charge, and a sphere, and the electric field from a charged sphere. We have done these three, okay? What we are gonna do next time is gonna be, instead of an infinite line, we'll do a finite, which is more practical, obviously, all right, than an infinite. And we'll see how the length then of the line changes anything. It's not gonna change the way the field changes. It's not gonna change that it goes like 1 over the distance, but it's gonna change the value of the field, if you like, all right? Not the way it changes with the distance. And then we are gonna do an interesting 3D problem, which is a charged ring. Why is that important? Because if you see how we create inductors, inductors are created from like rings practically, all right? And yes, we make them and they're long and they have an inductance, as we will see next, but also if they have a parasitic capacitance, your inductor is not gonna become a good inductor. As a matter of fact, because you're gonna have a combination of the inductance of the inductor and the parasitic capacitance because of the field. You remember, charges create fields, electric fields, which then give rise to capacitances, all right? So if you have an inductance and a capacitance, what happens? Do you remember from simple circuit theory? They resonate. So it goes and changes. What happens at resonance? At very, very low frequency, it looks like an inductance. When the frequency goes up, it starts to look less like an inductance. That is going to be at some point, there is going to be either 0 or infinite. The circuit is going to behave like a short or an open. And then above that, it's going to look like a capacitor. So you design an inductor, it looks different. And therefore, your circuit is not going to work. All right. So that's why it is important then to know the charge ring, because, you know, it's like a charge loop, if you like. That is going to help you with understanding the parasitics from that. Any other questions from today? So to summarize, read the problems well. Number one, pay attention to that. Don't rush to write a solution. Try to learn to understand what the problem is asking you. And then write down the things you know, which are related in your mind to this problem. Write them down. That is going to help you, even if some of those things may not necessarily be useful for that particular problem, but you know that you know those things. And then you start the solution, all right, to solve. And then you will see that your solution is going to evolve and it's going to come out much easier if you follow that approach. Okay, thank you. I'm going to assign you I'm going to assign you a quiz instead of an exit. Well, today is Friday. Yeah, a quiz. I'm going to assign you a quiz. And I will assign, of course, it's the same for both sections. And let me go and show you. So we go here. We close that. We open the quiz. Okay. All right. This is an interesting problem. Think about it. You have time, all right? It says the following. It gives you two functions, f of x, p of x. You see the functions in their form. And say, which of the following combinations? So in one, for example, there are two entities, charge and electric field, all right? Think of that charge and electric flux density will be the same kind of thing. One of the functions shows a possible charge and the other function shows a possible, the respective electric field or electric flux density. All right, remember the electric field and the electric flux density are related by a constant only. So knowing the relationship, Gauss's form, Gauss. This is in fact also a one-dimensional problem, all right, obviously. Remembering Gauss's law and then say which one of those two, F1 or F2 could be the charge and which one could be the resulting field, all right? No math, nothing, just think. Okay, thank you, I will assign it. Homework assigned, and I will do it for the other class.
Professor.
Yes.
I was
Hearing,
the microphone.
Are you speaking with me?
Yeah.
I cannot hear you very well because of the noise in the class. Could you send me your question in the chat?
Sure. Or whatever. So like, let's say you have as well.
Yes, I will take care of this. Let me look at this again. Justin, is it Justin?
Yeah.
Okay, yes.
Yeah.
I will send you an email. Yes.
So mine was, you had on ours that was like, it wasn't explained well enough. And
How much did I give you guys?
35 out of
35.
Yeah.
Okay.
I don't know if it would help if I show you and maybe, I'm not like trying to fight for points, but I just want to see if I was wrong or right or what's going on.
Okay, yeah, definitely.
And
Let me just turn this off. Yeah.